Okay, so this is the walkthrough of the second half of AQA A-level Chemistry Paper 1. This is the 2017 paper. The first half of this paper, question 1 to 5, was covered in another video. Okay, so question 6 about period 3 elements and their oxides. An equation for the reaction of phosphorus with an excess of oxygen. Well, phosphorus is going to give you P4O10. Really, we should write phosphorus as P4 because that's how it exists, but they will let you write down 4P if you look at the mark scheme. You don't need state symbols really, and then we're going to need 5 O2s. So it's all about knowing the formula of the, if you know that, then you're all right. Okay, describe a test you could carry out in a test tube to distinguish between sodium oxide and the product of the reaction here. Well, the background is, of course, sodium oxide, when you dissolve it in water, will give you sodium hydroxide, which gives you pH of about 14. Whereas P4O10, when you dissolve that in water, you get phosphoric acid, which will give you pH of like 0 to 1. Okay, so a test, you wouldn't write that in the question, you would just write down, you'd add a bit of water to the test tube, to the product, and then you'd test with a universal indicator, or any indicator you like. Universal will be the best, and you know, this one is going to be purple and this one will be red. So that would be the easiest way of doing that. Okay, the kind of crystal structure shown in silicon dioxide and sulfur trioxide. Okay, so silicon dioxide is giant covalent, very like diamond if you remember. Sulfur trioxide, it is simple molecular. Once again, they don't like simple covalent there. Simple molecular is what they want. Okay, why has silicon dioxide got a higher melting point than sulfur trioxide? Well, in SiO2, it's giant covalent. So if you want to melt it, you need to break covalent bonds, which requires a lot of energy. You get 2 marks for saying that, probably 1 for the covalent bonds, 1 for the lots of energy. If you want to melt sulfur trioxide, SO3, you're only breaking weak intermolecular forces, and they are van der Waals forces. SO3 is actually symmetrical, so there won't be any dipole there. So you're only breaking van der Waals forces, and they're weak, and you don't require much energy. So 2 marks for each. 1 for the nature of the thing you're breaking, and 1 for the amount of energy that you require to break it. Okay, right. 6.5, the reaction of sulfur trioxide with potassium hydroxide solution. Right, now, the easiest way to think of this, if you get sulfur trioxide and you react it with water, you get H2SO4. Okay, so the salt between sulfuric acid and between potassium hydroxide, well, it's going to have a formula K2SO4, isn't it? Because its sulfate has got a 2- ion on it. Right, now you get the same thing if you react SO3 with potassium hydroxide. It's an acid-based reaction. The SO3 is actually not a Bronsted-Lowry acid. It's just going to be a Lewis acid actually. Right, so, and you're going to get K2SO4. To balance that, we just need to put a 2 there, and then we will also make 1 molecule of water as well. You see there. So we get it's a neutralization. So we get a base plus an acid, and we're getting a salt and water. Okay, now a very similar one here, the reaction between the excess of magnesium oxide and phosphoric acid. Okay, so we've got magnesium oxide, MgO, so the magnesium ion is present there as an Mg2 plus ion in there. We're just thinking about the salt we're going to get, because this is a base and phosphoric is an acid. Right, we've got H3PO4. So the formula of magnesium phosphate, the phosphate ion there obviously has got a charge of 3 minus. So magnesium phosphate must be Mg3PO4 2. You have 6 positive charges and 6 negative charges. So let's balance that. So you're going to get, right, that we get MgO. You need 3 of those. Phosphoric acid, we're going to need 2 phosphoric acids, H3PO4, to get the salt. And that means we are going to be left over with 3 molecules of water as the equation. So again, we've got a base plus an acid goes for salt and water. And it's interesting, if you reacted it with P4O10, okay, you get the same salt there. You get magnesium phosphate again. It's worthwhile remembering that. They quite often ask that question. 6.7, draw the displayed formula of the undissociated form when sulfur dioxide reacts with water. So you should know then that SO2 reacts with water to form H2SO3, which is either called sulfurous acid or sulfuric 4, because that's the oxidation state of the sulfur. Right, so, and that is actually a weak acid. So what's the bonding in that? Well, if normal sulfuric 6 acid, you probably know, is like that. Sulfur can form up to 6 bonds. It's in group 6 of the periodic table. Oxygen always forms 2. So sulfuric 4 acid is just the same, but you've only got 1 oxygen there. Okay, so that is the displayed formula showing every bond. And of course, these are the 2 acidic protons there. Yeah, that can fall off. Right. And this one is about complex ions. Solution contains the compound, this compound here. Okay. Now, so let's just break down what we've got there. We've got copper H2O 6, 2 plus, the hex-aqua ion, complex ion, and we've also got 2 chloride ions in solution. They'll be completely separate. Right, what is the type of bond between the oxygen and hydrogen in this compound? Well, you've got a water molecule, that's just straightforward covalent. It's not dative covalent, just a normal covalent bond. So state why the chloride ions in this compound are not considered to be ligands. Well, it's because the waters are the ligands, because they're the ones which are forming the dative covalent bonds. That's a dative bond, that ligand to the central copper ion. So I'll just say here that the chloride ions are not forming dative covalent bonds or any kind of covalent bond to the metal ion. And that's what a definition of a ligand is, something that forms a dative bond to central metal ion. 7.3. An excess of ammonia is added to the sample of solution A to form solution B. So all that's going to happen there is the copper hex-aqua ion, you're going to get a ligand exchange reaction there. Right, if you had an excess of ammonia, right, if you had a little bit, then the ammonia will just pull protons off the water ligands and you get the precipitate. If you ever had an excess, you end up getting, you replace 4 of the water, and you just got to remember that. I don't know why it's not 6, but it's not. You only replace 4 of them. So 2 waters remain behind, and you've got 4 ammonias as ligands. And of course, the charge on the complex will still be 2 plus. We're going to need 4 NH3 there, and we are going to make 2 H2Os come off as well. Right, what color is this solution? It's very dark blue. So the copper 2 plus hex-aqua, this one is light blue, the color of copper sulfate, and this goes a really dark blue. Right, aqueous sodium carbonate was added to another sample of solution A to form a blue-green solid. Now, we have got this reacting. How is that going to react with the carbonate? Now, if you've got a 3+ ion there, a metal 3+ ion, they are stronger acids because if you've got 3+, the metal is more electron withdrawing. That's a strong enough acid to give protons to the carbonate ions, and you get CO2, so you get effervescence and water. That doesn't happen with this one because it's only 2+. It's not a sufficiently strong acid, so all that happens is you form a precipitate of copper carbonate. It's an insoluble compound, and to balance that, you're going to get 6 waters coming off. Yeah, but you don't need to do that. We need to identify the blue and green solid, which is that. It's a precipitate of copper to carbonate. So a different reaction with the 2+ ions compared to the 3+ ions there. Reagent D was added to another sample of A to form a yellow-green solution. So we're adding it to copper, and you should know this. How can you turn blue copper 2+ ions in solution to a yellow-green? Well, that's if you add chloride ions, and they will replace the waters. The chloride ions will act as a ligand. So let's write the equation first. So you get CuH2O 6, 2+, and it's only 4 chloride ions. If you remember, the chloride ions are bigger ligands, so you can't fit 6 around. You only fit 4, and so the formula of the complex is CuCl4. Right, you've got a 2+ on the copper and 4 minuses on the chloride, so it's 2- overall, and you will get 6 H2O molecules released there. They'll be replaced by the chloride ligands. And the reagent, right, to do this, you need quite a high concentration of chloride ions, so you would use concentrated HCl. That would be how you would have to do that. Okay, right, let's move on. Now, this is a tricky question. Why colorimetry can't be used to determine the concentration of solutions containing CuCl2-. So if you look at that, well, and this is not something you will be familiar with. Each of those chlorines is minus. So that means the oxidation state of the copper there is +1. It's copper 1. If you remember if you remember copper 1 ions, they have a full D shell. It's a D10, 3D10. And if something has got a full D shell, like copper, also like Zn2+, copper 1, not copper 2, like Zn2+, you can't. The compounds are colorless because you can't get promotion of electrons from one d orbital to another. Okay, for the 2 marks there, I think you just have to recognize, say that it's copper is, you've got copper 1+ ion, and the electronic structure of that is 3D10. It's a full D shell. You don't have to explain any more, really. Just to remind you that, of course, copper itself is argon core 3D9 4s1. Sort of borrows one, but the copper 1+ ion is 3D10. It's got a full D shell. I suppose you just have to know that. And copper 1 compounds are frequently not colored. Right, this is about a question about ion testing. How could you distinguish between solutions of potassium nitrate and potassium sulfate? Right, okay, the easiest way there is, of course, is just test for the sulfate ions. So you test for that by adding barium chloride solution, or you could use barium nitrate, and you should acidify it with hydrochloric acid really as well. And nothing will happen there. No change, no visible change. You're not forming any insoluble precipitates. With potassium sulfate, though, you will get a white precipitate, and because you will form the very insoluble barium sulfate. Okay, so that's your 3 marks. The reagent, 1 mark for the reagent, barium chloride and HCl. Let's say solution, barium chloride solution in the safe side, and dilute hydrochloric acid. No visible change, 1 mark, and white precipitate, the 2nd mark. Right, how could you distinguish between solutions of magnesium chloride and aluminium chloride using one simple test tube reaction? Right, you can't test for the chloride ion because they both got them. Well, an aqueous solution of aluminium chloride, you're going to have AlH2O 6 3 plus. Now, if you add NaOH to that, first of all, you get a white precipitate of Al. So you've removed 3 protons, H2O3 OH3. Be no charge on that complex ion. And then you add excess that will redissolve to form a colorless solution because you actually form AlH2O2. You remove another proton, so it's charged now, negatively charged. You form that. So that will happen with aluminium. You get a white precipitate which will redissolve to form colorless solution. When you add excess. Okay, now what will happen if you add, oh, what are we adding here? Okay, so don't say what we're adding. We're actually adding sodium hydroxide solution. What will happen if you add sodium hydroxide to magnesium chloride? Well, you probably recall group 2, magnesium hydroxide is very insoluble, so you'll get a white precipitate of magnesium hydroxide. That's not an observation, no, just a white precipitate, and that will not redissolve. It won't redissolve, even if you add lots and lots of excess sodium hydroxide. So add sodium hydroxide, white precipitate in both cases. The white precipitate in the case of aluminium will redissolve. Right, I'm giving you a bit more background here. Obviously, you don't need to write all this in your answer. I'm just trying to explain. So I'm not just giving you some, you can see where the answers are coming from, but you don't need to write all that, obviously. Okay, this 6-mark question is a bit of an unusual question. It's a bit like a GCSE equilibrium question, really. Okay, so you've got making methanol. The first stage involves a gaseous equilibrium. Okay, they don't even give you the equation, but don't worry. Reacting methane and steam. Okay, and you get gaseous products. Shows the percentage conversion. Okay, so this graph here, this is the percentage conversion to methane against temperature, and here percentage conversion to methane against the pressure. Deduce the optimum conditions for the industrial conversion. Explain your deductions. That's a 6-mark question. So what I would say is, right, let's talk about temperature first of all. Right, you would probably use, there's no point using a temperature higher than about there because you don't get any increase in yield. So you want the temperature of approximately 800 degrees C, and say why you wouldn't go any higher. There's no point going higher. Going higher will cost money, will be expensive. So that's why you'd use the, okay. Also, you might want to say that 800 degrees is a pretty high temperature, so you are going to get a fairly fast rate of reaction there. Of course, rate of reaction and equilibrium are not related at all. But you do want to, you want it to reach equilibrium quickly. You don't have to wait ages, so you want a fast rate of reaction. So I'd say those 3 points for temperature. Now for pressure, as you increase the pressure, the yield goes down. Obviously, you're making more gas moles in products. So you don't want the pressure to be too high. Not too high because you get a worse yield. So the yield is going to go down. But you probably do want to use a moderately high pressure, because if the pressure is too low, I don't think you have to put a number on that. If you look at the mark scheme, they're very generous. You can say whatever pressure you like, really, but you do need to say moderately high, because otherwise the rate of reaction will be too low. Of course, if you with a gas, the pressure is really like how concentrated the gas is. So the particles all closer together, the rate of reaction is going to be faster. So that's what I would say for that question. Right. Now here we have got, Equation shows the final stage in production of methane. You've got to calculate the amount of moles in carbon monoxide and hydrogen in the equilibrium mixture. So let's write down the equation. I'll write it here. So we've got carbon monoxide. Right, I'm going to write down start moles. Moles used up. Some people leave the moles used up, but I like to put it in an equilibrium moles. And then we write the equation here of carbon monoxide plus 2H2 going to methanol. Okay, start moles, we says we've got 2.1 carbon monoxide, 24.2 hydrogen, and we haven't got any methanol. At equilibrium, you've got 21.6 moles of methanol. Well, look, 1 mole of carbon monoxide gives you 1 mole of methanol. So, sorry, 20.1, I should say, not 2.1. So, 1 mole of carbon monoxide gives you 1 mole of methanol. So that means the moles used up is going to be, sorry, that's 2.16 as well. So to make 2.16 moles of methanol, you must have used 2.16 of this. Subtract that to get the moles left over. 20.1 minus 2.16. That is going to give you that gives you 17.94. So that's the moles of carbon monoxide. Now, if you've used up 2.16 of carbon monoxide, you must have used up 3 times 2.16 of hydrogen. So that means you've used up 6.48. So how much you got left? You do 24.2 minus 6.48, and that gives you 17.72. So there's your, so we've got our answers there. The moles of carbon monoxide is that much, and the moles of hydrogen is that much in the equilibrium mixture. Right, now as usually the case with these questions, the next bit it says in a different equilibrium, a different mixture was allowed to reach equilibrium. Okay, and they give us these moles of carbon monoxide, and we have got to work out Kp. So what's the expression for Kp then? Well, Kp is equal to partial pressure of methanol to the power of 1 divided by the partial pressure of carbon monoxide to the power of 1 multiplied by the partial pressure of hydrogen. We've got 2 moles of hydrogen, so it's squared. Okay, now what are the units of that equilibrium going to be? Well, we've got Kpa on the top, Kpa on the bottom, and then we've got Kpa squared on the bottom. They cancel out, so it's 1 over Kpa squared, so that's the units of Kpa to the minus 2. Okay, now let's actually work out the numbers. Right, so we need here, right, we're running out of space here, I think. Okay, so we need to work out, first of all, mole fraction. So here's our gases. We've got CO, H2, and methanol. And we need to work out the mole fraction. I use that little lambda sign, mole fraction. But we need to work out the total moles first. Well, the total moles is 2.76 plus 4.51 plus 3.36, and that is equal to 7.63 moles. So the mole fraction of carbon monoxide is 2.76 over 7.63. Of hydrogen, it's 4.51 over 7.63. And for methanol, sorry, it's 0.36 over 7.63. Right, now the partial pressures, well, what we've got to do is you multiply by the total pressure, big P, which is 630 kilopascals. So for what we do is times that by 630, multiply that by 630, multiply by that by 630. Right, you put all those numbers into that equation on your calculator, and you get the answer. If you want to make things a little bit easier, I don't know, you just save a tiny bit of time, you can do a bit of cancelling out. So I'll just show you how you could do that. So you could have Kp is equal to the mole fraction of methanol. So let's do that's 0.36 over 7.63 multiplied by the total pressure. I'll just call that P. That's the partial pressure of methanol. All right, divided by 2.76, for this is the carbon monoxide, over 7.63 multiplied by the total pressure, which is big P, and then multiply that by, for hydrogen, we've got 4.51 over 7.63 multiplied by big P, and I'll put that in there, that's 630, and we need to square all of that. You can probably see then that that and that cancel out, and those cancel out, so you can, it does make it a bit easier. You get the same answer, and the answer is, you should get 9.41 times 10 to the minus 7. Okay, we worked out the units before were kilopascals to the minus 2. Okay, so that's that question done. Okay, we've got an electrode potential question coming up here. All right, so right, let's just do the oxidation state of nitrogen NO3. Well, the sum of the oxidation numbers is equal to the charge on the species. Let's do nitrate first of all. The charge is -1. Let's let the oxidation number of nitrogen, let's call that N. Oxygen, of course, is always -2, so that's -6 for the oxygens. So just take that -6 to the other side. Nitrogen is +5 in that. And in NO, charge on the oxidation, the charge, okay. The charge on NO is 0. So we have N -2 for the oxygen. So the oxidation number of nitrogen then is +2. Right, okay. Right, now let's have a think about the electrode potentials and stuff. Okay, state the weakest reducing agent in table 4. Okay, let's have a look at this then. So what do reducing agents? They give away electrons. So which is the best reducing agent? Well, so first of all, which things can give away electrons? Well, it's things on this side of the equation, the right, because when these little equations go backwards, they give out electrons. Okay, so that right-hand side is all potential reducing agents. Which is the best one? Let's look at it this way. Which is the best reducer is going to be the one that pushes away electrons the best. What kind of things push away E minus the best? Well, the most negative one, because electrons are negative, and so the most negative thing. So the best reducing will be this one here because it's the most negative. So iron metal is the best reducing agent. The question doesn't ask that one; it asks the worst reducing agent. So it's this one up here, which is the most positive. It's the chloride ion. That is the worst reducing agent because it is the most positive. So it's actually not very good at pushing away electrons because it's positive. It tends to draw them in. Okay, that's the way I would describe it, explain it. Of course, you don't need to explain it, you just need to state it for 1 mark, but there we go. Right, next part of this question then. Right, write the conventional representation of a cell that has an EMF of 0.43 volts. Okay, so we have to remember that E cell is equal to E right, which is the most positive by convention, minus E left, which is the most negative. So you can see if you just get one more positive and subtract from the other, you can probably see, I saw pretty quickly that these two, okay, will give you that. So the iron one is 0.77, take away 0.34 is going to give you the plus 0.43 volts, which they require. Right, but it asks us to write the conventional representation of the cell, that is the AMF of 0.43 volts. So, which is the most positive of these? It is the iron, and this is the most negative. Now, you draw your salt bridge as a dotted line, and the convention is to put the most positive on the right. Okay, and then you put your two species in. Now, I will write down Fe3 plus next to the salt bridge, because of course it should be the most oxidized species that goes next to the salt bridge. And then I'm going to do a comma and Fe2 plus. I don't draw a straight line because they're in the same phase. They're both in aqueous solution. And of course, you don't have any metal there. You've got metal ions, but you haven't got any metal as an element to conduct. So you're going to need some platinum there. So there is a phase change of platinum, a straight line, and PT. And then the copper one we represent, that's the most oxidized. So Cu2 plus goes next to the salt bridge. We draw a phase change because they're in aqueous solution. The copper metal is solid, and we don't need platinum there because we've got copper metal. So that's the conventional representation of the cell. That's the answer to that question. Right. Okay. If we move on now to, I've pasted in the electrode potential to gain for this question there on the right. He says we've got to identify an acid that will oxidize copper metal. So first of all, we want this equation here, don't we? And we want to oxidize the copper, so we want to make it go backwards. We want to make it give away electrons. So we need something. So the copper is going to be the most positive and give away the electrons. So we need one which is more positive than the copper 2 plus copper. Right, so we look at, right, all acids contain H plus. Well, can H plus ions, can they react with copper metal? Can that one go forwards? No, it can't. That and push the copper backwards, that can't happen because this one is more negative. So that's actually not very good at pushing away electrons. It's not as good at pushing away the electrons as the copper. So it can't make the copper except, sorry, it's not very good at taking in electrons. It can't take electrons from the copper and make the copper. It can't do that. Right, let's see. So sulfuric acid, that's another acid we've got there. We've got sulfate ions. Right, I'll just clean this up a little bit. Right, so can the sulfate ions get reduced to SO2 and oxidize the copper? Well, you can't. You can see that it's going to be the copper one which goes forwards most readily because that is the best at taking in electrons. It's the most positive. It's not this sulfate one. It's not as positive. It's not as good at doing that. Right, so now let's look at the nitrate, because nitric acid contains NO3 minus ions. So can this one go forwards and make the copper go backwards? It can. This one is more positive. It's better at taking in electrons. It will take in electrons. The copper is more negative, so that's better at pushing away electrons. That will go backwards. So nitric acid will do it. Right. Let's just, for the sake of completion, why can't hydrochloric acid do it? Well, that is because, well, chloride ions, you need a potential oxidizing agent, don't you, to make that go backwards? Well, chloride ions are not a potential oxidizing agent. If anything, they're a potential reducing agent. So that wouldn't work at all. So nitric acid is the answer to that. Right, calculate the EMF of the cell. That would do that. So we need to look at the two E cells we need to look at. We need to look at the copper one, and we need to look at the nitrate one. E cell is equal to E right minus E left. By convention, the right hand is the most positive one, which is the nitric acid one. So that's nitrate one, sorry. So that's plus 0.96 minus the copper one, 0.34. That's equal to plus 0.62 volts. Okay, so that is the end of that electrode potential question. Now, this question here, you may have seen this before. It's one of the hardest titration questions I think that they've asked in recent years. Okay, and I think there's a lot of marks. I think it was a 7 marker. I'll cut that bit off, but it was 7 marks, I think. Right. Okay, what we got here, we've got a mixture of ethane dioate and ethane dioic acid. Okay, and you're going to carry out 2 titrations of this. The first one, right, you add some sulfuric acid. The reason why you do that, this is the equation for the first one. You add sulfuric acid, excess, put it in a conical, you put your these 2 in a conical flask, and you titrate in your purple manganate here, okay, until, and as it goes in, that's colorless, and the end point, of course, when you got your, don't worry about that. Right, so let's look at the ratio in that. Let's look at that first equation then, that first titration. That is going to react with both of these. Manganate reacts with both. So that's going to give you the total moles of the sodium salt and of the acid. They both contain this ethane dioate ion, and that reacts in a 2:5 ratio there. So the ratio of manganate to these 2 is 1:2.5. So let's work out how many moles of manganate we've got there first of all. Okay, so moles MnO4 is concentration times volume, 0.02 multiplied by the volume, 26.5 over 1,000. That gives you a number of moles of 5.3 times 10 to the minus 4, moles of manganate. So therefore, the moles of the ethane dioate, of the sodium ethane dioate, and of the ethane dioic acid is equal to 5.34 times multiplied by 2.5, because that's the ratio, and that gives us a number of moles of, I have to go down here a bit, a minute. So the total number of moles of these 2 in 25 centimeter cubed, let's write that down, that's how much they put in the flask, in the conical flask, is that times 2.5, which is equal to 1.325 times 10 to the minus 3. That's in 25. So, but that, we only took 25 out of the volumetric flask. The whole total amount was 250. So therefore, in 250, the moles of those 2, I'll write it down again, and of the acid, H2C2O4, multiply this number by 10, we get 0.01325. And we're going to use that later on, that result. So I'm going to put a circle around it. Okay. Now let's get on to titration 2. Now titration 2, all right, we'll do it here. Okay. Titration 2, we'll just rub this bit out here. Make a bit of space here. I'm going to drag this down out of the way. It lets me. Yeah. Right. Okay. So here, titration 2 is only going to pick up the ethane dioic acid. It's not going to detect the sodium ethane dioate. Sorry. Right. So ethane dioic acid reacts with sodium hydroxide in a 1:2 ratio. Okay, and it says here we've got 25 centimeters cubed of the solution, react with 0.1 of sodium hydroxide, and we needed 10.5 of the sodium hydroxide. So let's do moles of NaOH is equal to the concentration times the volume is equal to 0.1 multiplied by 10.45 over 1,000, and that is equal to 1.045 times 10 to the minus 3 moles. Right, Now it's a 1:2 ratio, so therefore to get the moles of ethane dioate, ethan dioic acid, that's in 25 of course, we are going to have to do that number divided by 2. So 2:1 ratio, and that is equal to 5.224 times 10 to the minus 4 moles. And that, of course, is in 25 centimeters cubed. So in 250, which is the total mass, the total volume we had, so moles of that in 250 is going to be it's going to be 5.224 times 10 to the minus 3 moles. Now we've got these two intermediate answers here, and then we're going to do the final bit. So I'm just going to paste these in here. So here's our two results from titration 1. We say we've got that. Okay, and in titration, so that's titration 2. In titration 2, we found out that we had this moles of the sodium salt and the acid combined. Okay, so I'm going to put that down here. Right, we're going to use these two results here for the final bit. Okay, now for the final bit, I've just pasted this bit out again. You say here we've got the white solid is a mixture of the sodium ethan dioic and the acid, and also an inert solid, and we made that at 250. Okay, so what we're going to do is we're going to find out by subtraction this is our moles of sodium. Oh, sorry, this is the moles of ethan dioate alone. This is the moles of ethan dioic acid plus the sodium salt. So we're going to write down here moles of sodium ethan dioate only is going to be equal to that red number minus that blue number. I'll do that in green. That gives us an answer of 8.026 times 10 to the minus 3 moles. Now we need to work out the mass of that. So mass of the sodium ethan dioate is equal to the moles times by the MR. We work out the MR of that, it works out to be 134. Okay, so let's put that in 8.026 times 10 to the minus 3 multiplied by 134. That gives you 1.075 grams. Now, what is our percentage of sodium ethan dioate by mass? Well, it's going to be that divided by the total mass, which they said here, I've just covered up, they said was 1.9, I think. Yeah, we've got 1.9 there, can you see it? Over 1.9 multiplied by 100, that gives 56.6%. Okay, so you have to work fairly hard. A few marks for that question. It's quite a difficult one. Okay, so that is the end of the paper.